Hello everyone. Today we are going to cover one of the most important algorithm in the information retrieval, which is the locality sensitive hashing for the near duplicate document detection. Let me start with the background. About 10 years ago, studies shows that roughly one third of the entire web was duplicate content. So this is a massive problem that affects the search engines, storage systems, and the user experiences. But what exactly do we mean by duplicates is that there are mainly two types of the duplicates. So one is the exact duplicate and the other is the near duplicate. Um, so exact duplicates are the documents that are identical bit for bit. Like if you do a string comparison, they are exactly the same. So sometimes the non-content elements might differ, like ads or navigation, but the core content is identical. Coming to the near duplicates, these are much more challenging when compared with the exact duplicates. These are the documents where the bulk of the content is the same, but there are small changes. So think of a student who takes like another student's essay and changes a few words, moves sentences around, and inserts a different adjectives. So the essay is still very much the same, but it has been slightly removed. So where the near duplicate is 90% of the content is the same, but use the different keywords. So here, the first approach is that we have to detect the duplicates naively. It is a naive approach, so which has the quadratic complexity, time complexity. So here we compare the every document along with the against all other the documents. So here is the algorithm you can see, and the complexity, computational complexity is around order of n squared d, which is the quadratic complexity and which is very much impractical. So where n is the number of documents in a set and d is the size of each document. Here we get the quadratic complexity because we have to compare every document against all other documents. So this is the naive approach and it is very much impractical. Coming to the another approach, here this is the duplicates via naive approach. Here it is the via fingerprinting approach. So, so a much better way is to detect the exact duplicates is through hashing and the fingerprinting. Here is the high level idea. You will maintain a hash table indexed by the fingerprints for every document in your collection. You compute a fingerprint which is a larger number that should always be the same. Like if the two documents are identical, you insert document into a bucket of the hash table. So when multiple documents fall into the same bucket, you know that they have the identical fingerprints. So which means they probably have the identical content. So you insert the documents into a bucket in a hash table. So now what if two different documents accidentally get the same fingerprint? So this is called a collision and we have to test it if it has a duplicate or not. So this is called a collision. It can happen because you are mapping a huge amount of the text to a finite number of fingerprints. So but it is not a problem because once two documents land in that same bucket, you can do an exact test to verify if they are truly duplicate or not. So the beauty of this approach is that the linear complexity, you are not comparing every document to all others. You just compute fingerprints and then do a small number of the comparison for colliding documents. So this is the beauty of this approach. We are the fingerprinting is that we'll make the duplicate fall into the same bucket in the linear complexity. And coming to the next, here is the Adler 32 fingerprint example. Like, let me show you how to compute the fingerprints using the Adler 32 algorithm with a concrete example. So we will use the string, suppose a cab. So as our example, and then the algorithm goes through the string character, character by character, including the spaces and taking the integer values of every character, and maintains two cumulative sums, which is sum b and sum a. We will start with the character A in the A cap, which has the ASCII code of 97. The running sum B is the running sum, and sum A is the cumulative running sum. So the running sum becomes the 97 and the sum of the running sums A becomes the 97 here. Coming to the next character is a space with the ASCII code of 32. A becomes 97. Um, the running sum becomes the B becomes 97 plus 32. So which is equals to 129, and A becomes 97 plus 129, which is the running sum. So which equals to 226. And then coming with the next character C with the ASCII code of 99. So if A is the 97, then B will be 98 and C will be 99. So the B becomes 99, 129 plus 99, which is equals to 228. And the A becomes 226 plus 228, which is the running cumulative sum. So which is 454. Like we continue the process for all the characters. At the end, we have two large numbers, A and B. So what we will do is we then take these sum modulo a large prime number. So for 32-bit hashes, we use 65521 as the large prime number, which is the largest prime number, which is less than 65536. And finally, we combine them and we take a modulo prime shifted by 16 bits and do a logical OR with the B modulo prime. So the result is our 32-bit fingerprint. So the key property of these fingerprints is that when a single byte in the input changes, entirely the checksum changes dramatically. This is by design for the data integrity applications. So it will add up a byte value and modulo a prime. So magnify small changes to the input. For the data integrity applications, the even the small input changes, the entire checksum will change dramatically. So it is for the data integrity. And then coming to the, it is same as this and same example. So coming to this overview, what the project is all about, the locality sensitive hashing, and we will compare it with the traditional hashing first. So it is a technique that for a similar inputs, it would with a high probability create outputs that fall in the same bucket. We have seen in this example via the fingerprinting. So whereas unlike traditional hashing where we aim to minimize the hashing collisions, for the locality sensitive hashings, we strive to maximize the collisions for the similar items. Coming to the traditional hashing, we try to minimize the hashing collisions. So here is the comparison for the traditional hash function, simple hash function. These are the hashing functions, and for the locality sensitive hashing, we will try to group the similar values together. Here, if we see 1 and 2 will be grouped to the 1, 3 and 4 grouped to the 1. So we will try to group the similar values close together. And coming to the distance measures, so our goal is to find the near neighbors in the high dimensional space. So we formally define near neighbors as points that are small distance apart. So coming to the Jaccard distance or the similarity to measure how similar two documents part, we use the Jaccard distance or the similarity. The formula is pretty much simple. So it is the size of the intersection divided by the size of the union of the shingle set. So if we compare these Venn diagram, we can see the intersection point of these two charts is 3 and the union is of 3 and 4, which is 7. So the similarity will be intersection by union, which is 3 by 7, and the distance will be 1 minus 3 by 7. So the task is to finding the similar documents. Suppose we have given a large numbers, say n is the millions or the billions of the documents, we have to find a near duplicate page. Uh, There are many much applications like mirror websites or the approximate mirrors. And problem is that many small pieces of one document can appear out of order in another. So also too many documents to compare the all page. These are the disadvantages because we have the large number of the n. So for this purpose, we have shingling. So we have three essential steps actually for the near duplicate documents: shingling, min hashing, and the locality sensitive hashing. Shingling is that for the near duplicate detection, we need a more sophisticated approach because small changes create a complexity, completely different hashes. The first step is shingling. Um, we will see an example for this shingling. Shingling is that converting the documents into a set, and min hashing is that converting the large sets to short signature while preserving the similarity. And locality sensitive hashing is that focusing on the pairs of the signature likely to form a similar documents. Here, similar documents is of candidate pairs. So this is the big picture of how our project works. We will give the document and then the first step is that shingling step. So here we will convert the documents into sets and then the set of string will be of the length k that appears in the document. After that, we will have a min hashing. So we will form a short signatures and we will preserve the similarity. And after that, we will have a locality sensitive hashing. We will focus on the pair of the signatures. And this is the big picture of how the locality sensitive hashing works. And then coming to the documents with the high dimensionality data. So shingling is that we have to convert the documents to sets. So simple approaches are the document set of words appearing in the document. So this approach is called the bag of words, and the document is that set of the important words. And this second is that also known as the stop words. And we have to account for the ordering of words. So we need to have a this is bag of words and this is stop words, but we need an ordering of the words. So that's where shingles came. And the shingles is defined as the K shingle or the K gram shingle for a document. It is a sequence of K tokens that appear in the document. Uh, the concept is that we have to represent a document by its content, like not just the keywords, by its content. So K shingles is defined as what they are, contiguous sequence of the K characters or words. We have to choose the K, like it should be the trade-off between, if we choose the larger K, we will have the more specificity. And if we choose the smaller K, we will have more false positives. So we have to hash the shingles afterwards. So we have to explain why we hash the shingles to integer because to save the space. Here if we see an example, we have the document ABCAB. Here k is equals to 2. If we take the k is equals to 2, then we have to make a two set of the shingles. So this is a set AB, BC, CA, and AB. As AB will be repeated two times, we also have an option like for the multi-set, we will count the AB twice. But for the normally, we will consider only one unique values. So coming to this example, the sky is blue and the sun is bright. We will assume the tokens as the words here. We assume the tokens as characters here. So if we come assume the tokens as words, like the k is equals to 3, then we say the sky is blue and then is blue and the. So likewise, we will convert all the text of the documents into a shingles. So based on the k. As said, if we choose the k higher, we will have much more specificity, and if we choose the k lesser, we will have more false positives. So likewise, we have to compress the long shingles, right? So we will have a larger text in the document. So we can hash them to the 4 bytes. So we will represent a document by the set of hash values. Why? Because to save the space. So the two documents could appear to have shingles in the common, where in fact only the hash values were shared. So if we say k is equals to 2, the similar example, we will hash them into 157 for the sake of simplicity and for the storage efficiency. The working assumption is that documents that have a lot of shingles in common have similar text, even if the text appears in a different order. So the caveat is that you must pick k large enough, or most documents will have more shingles. If say if k is equals to 5 is okay for the short documents, and k is equals to 10 is better for the long documents. So if we choose the higher k, we will have the much more specificity, and if we choose the shorter k, we will have the much more false positives. And coming to the motivation. So we have completed the shingling part. So coming to the Minhash signatures. So but comparing these large sets directly also is still expensive. So this is where the Minhash comes in. So Minhash creates the compact signatures that preserves the Jaccard similarity. Here is the magical property. The probability that the Minhash values for the two sets are equal, exactly equal to the Jaccard similarity. So let me explain how the Minhash works with a simple example. So imagine um, see, this is the same as we discussed in the Venn diagram. So the Minhash is the Minhash's value for the two sets. So this one is one set and this one is one set. So the Minhash value of the two sets is equal to the Jaccard similarity, which is 1 by 4. And for each, we will let me explain how the Minhash works with a simple example. So imagine we all have a possible singles in a fixed order and we randomly permute or shuffle them multiple times. So here rows are the singles and the columns are the documents. So one in a row E and the column S, if and only if E is a member of the S. So column similarity is the stack similarity of the corresponding sets. So typically, as the documents are much more like n is equals to from millions and billions, there will be a sparse matrix, like there will be lots of large number of the zeros in the matrix. So what we have to do is we have to find the similar columns. The next goal is that finding the similar columns with the smaller signatures. So the signature of the column is that small summaries of the column, and we have to examine the pair of the signatures. So the warnings is that comparing all the pairs may take too much time. So we have shifted to the we have shifted to the LSX from the Minhash. So if we um, see the min hash, finding the hash function such that the similarity is high if the probability is high, and the similarity is low if the probability is high, and the h of c1, which is the hash function, is not equals to h of c2. It is between the two documents, and clearly the hash function depends upon the similarity metric. And there is a suitable hash function for the Jaccard similarity, and it is called hash min hashing. So uh, we will see an example for the min hashing. So these are the shingles and these are the shingles in the documents. These are the permutation matrix. So let me show how this works. So for the two, we have one. So one. So from this permutation matrix, this is the min hashing, and coming to the locality sensitive hashing. So the hashing part, the rapidly narrow down the candidate pairs of the comparison, and the bands and the rows are technique. Split the signature matrix into B bands and the R rows. So coming to the locality sensitive hashing, not even with the min-hash signatures, we still have a problem with too many comparisons. That is where the locality sensitive hashing comes in. So LSS uses a brilliant idea. We take our signatures, vectors, and split them into bands. So, for example, if we have 100-dimensional signatures, we might split them into 20 bands of 5. So this is where the SIMHAsh, it is an efficient variant of the LSH. And so this is the LSH spanning technique. So For each band, we hash a subvector into a bucket. If two documents have identical subvectors in any band, they have to the same bucket and become the candidate pairs. So let me show a probability analysis. Assume two documents have the 80% similarity and we use 5 rows per band. So probability that the match in one band is that using the example, uh, we have an example 1 minus s power r and power b. So upon substitution, we will get the probability is 0.99965. So it is a chance of detection. For the lower similarity documents, the probability also drops significantly. Coming to the S curve, so the general formula of the LSS detection probability we have seen, and this creates an S-curve behavior. There is a threshold T approximately equal to 1 by B, raise it to 1 by R, where above this threshold detection probability is very high and below it detection probability is very low. So for example, if we take B is equals to 20 bands and R is equals to 5 rows, T is approximately 0.55, and so the documents with more than 55% similarity will likely be detected. So while those below likely be filtered out. So you can also tune the B and R based on your needs. More bands increases recall but might increase the false positives. So more rows per band increases precision but increases the false negatives. So we have to trade off between these two. So this is the problem. And this is where I said the P is equals to 20 and R is equals to 5. So with the more bands, we will have the false positives more. And with the more rows, we will have the more false negatives. So we have shown the S-curve graph with the probability and the similarity. Probability and the similarity. So this is the false positives and false negatives. Here we incorrectly flag the non-duplicates as duplicates, and coming to the false negatives, we miss the actual duplicates. So with LSH, we can control this trade-off through parameter tuning. So if we use 2-bit hash codes and 10 tables, we get zero mistake for the 80% similarity, but we get lot of the false positives because we only have 4 buckets. Coming to this, if we have a billion documents, each bucket would contain a 250 million potential matches. So while the miss rate is low, the computational cost would be horrendous and the false positive rates would be high. So this is all the summary we have discussed. So for the duplicates, we have discussed about the 30% of the web and the exact duplicates where the bit 2-bit is similar, and we have discussed about the quadratic complexity and also the fingerprint approach with the Atlas 32, which have the linear complexity, and for the near duplicate elements, only the sentences are changed, like the adjectives will be shared, but the content remains same. So we have seen the locality sensitive hashing fingerprint, and we have seen the sim hash and min hashing. So these are the summary of what we have discussed. Near duplicate shingling. Shingling is the representing the document by its content, like making keeping the value k gram index, where if k is equals to high, we will have the high specificity, and if the k is equals to low, we will have the more false positives. So we have to trade off between the k value, and this is the locality sensitive hashing, and this is the formula which we are discussing, and this is the Jaccard similarity set of intersection by the set of union. And coming to the summary, um, there are many real world applications for the LSH. So LSH is used everywhere in modern systems, like the Google search uses to detect or remove duplicate web pages. Plagiarism detection systems would use it to identify the copied content. Social media platforms use it to detect the reposted or the near duplicate content. Recommendation system use it to find the similar users or the items. Content delivery networks use it to save the storage and the bandwidth. So likewise, we have many real world applications. Coming to the evaluation metrics. So to evaluate our duplicate detection system, we will use a precision and the recall metrics. So precision measures of all the document pairs you found how many were actually duplicates. like the actual duplicates by the true positive plus false positives. Coming to the recall of all the actual duplicates in the data set, how many did you find? And FN score is the harmonic mean of the precision and the recall. And the precision recall trade-off is that explaining how changing the LSH threshold, like the B and R bands and the rows, affects these metrics. A lower threshold increases recall but may lower precision. So this is the summary of what we have discussed and how we can detect the near duplicate documents with the locality sensitive hashing. Thank you.